These notes are on section 2-3 of your Walker textbook. So we're broaching the subject of acceleration, which is a change in velocity. Technically, it could be a change in speed, but it could also be a change in direction. In this case, we're really just talking about a change in velocity, in a change in speed. And then we'll get to a change in direction later in this textbook. So here is a definition of units too. So acceleration is a vector quantity, which the direction of it, or sign, is going to get a little bit confusing, but we can clear it up. And then units are going to have distance in the numerator and then some form of time squared in the denominator. So most often we're using meters per second squared, or sometimes called meters per second, okay? Because if you're talking about velocity is in meters per second, and then that's changing, so it's a rate of change of a speed, then you're going to have seconds again, okay? Or you could even talk about, if you're talking about a car that's going a certain miles per hour, and then it's speeding up in seconds, you could even have a couple different units of time, right? So you could have meters or miles per hour per second as a unit of acceleration. Okay, so we use that less often, but it's certainly valid. Okay, and then as we talk about average acceleration, then we are gonna, just like we did average velocity as the change in position over the change in time, here we're gonna talk about average acceleration as the change in velocity over the change in time. So if we're looking at the velocity time graph here, I pasted this graph in again. We could look at the average acceleration as the slope of a velocity time graph when that is a linear function. So here we see, I think this was an elevator. If the elevator is speeding up at a constant rate, then it has a constant acceleration. And we could take the slope of this line and we could get that acceleration just by doing delta V over delta T. Also here, we could get this acceleration on the slowing down side, okay, by doing slope of this line or segment to get acceleration. You can also do that for any velocity function, even if it's not linear, but you have to understand that it's just an average over time. Okay, and then referring to that, if you have a nonlinear velocity function like this one, it's very small, but this blue line here, curve, is a velocity as a function of time. It isn't linear, but we could find the instantaneous acceleration of this object, okay, by taking the tangent line at any point in time. And so if or the slope of the tangent line, I should say, okay? So we could find the slope of the tangent line, and that would be, in calculus terms, the first derivative of the velocity function, and that gives us the instantaneous acceleration, okay? What is the rate of change of velocity of this object right now, okay? And that's what we refer to as the instantaneous acceleration. So this is nice and smooth, okay? But when we looked at the motion detector graphs, right, of your motion in our lab, those were really noisy graphs. And if we tried to get acceleration from those would be really all over the place. Or for real life objects, sometimes this is really a much more complicated thing to get. So it could get much more interesting, but we're going to probably stick with some more simple functions, okay, where we're taking the first derivative of the velocity function to get the acceleration at a moment of time. When we talk about acceleration, this is a real thing that your body can feel. It is what makes movement exciting. It's not really speed, honestly, that makes motion exciting. It is acceleration. So that's why I put the roller coaster picture in there. And when you hear folks talking about G's, okay, we're going to get into that later, but that's really just a multiple of how many multiples of the acceleration due to gravity are you feeling when you're accelerating. So G's aren't force, although they're related to it. They are really referring to acceleration. And too much acceleration is a bad thing for the body. But it certainly is what makes rides or experiences like that fun. Okay. Now, let's talk about sine, okay? Because we said that acceleration is a vector. And so it has a magnitude, an amount, and it has a direction, which we, in physics, we give that a positive or a negative to indicate the direction of the vector. But that gets a little bit confusing because most people would like to say, oh, then negative acceleration, I would think that would mean like slowing down, right? Because acceleration should mean speeding up, and like negative acceleration would be the opposite, but it doesn't work like that. So what I want you to think of is this table, that anytime the two signs of velocity and acceleration match each other, that means that the thing is speeding up. And whenever the two signs of velocity and acceleration are a mismatch or are opposites, then the thing is slowing down. So you cannot associate negative acceleration does not equal slowing down. And we can practice this more, and we're going to be looking at some graphs and we can look at some cases of why is that. But for now, I'm going to leave it at this table, and you can copy this into your notes if you'd like to help you remember. Okay, so now I have this slide in here to remind me to tell you to go watch the video that goes with this sample problem so that you can be prepared to solve for the acceleration as a function of time using the power rule.